chapter 1, or is it only 2 through 5?
Yeah, only 2 through 5. There's no chapter 1. Yeah. But I'm not sure of how much of 5 we'll do. Maybe we'll do it all. Depends on, chapter 5 is not that long of a chapter, but we'll see. Chapter 1 is a part of the exam, yes. The scientific method. Yeah, basically the scientific method. All right, just before I erase this temperature stuff, another way of thinking about the temperature is this. You know, if you're looking at what mile marker you are, let's say you're driving on a trip and you're looking at the roadside, what mile marker, then you care about where the 0 is. You know, where was the start, 0. And so in this case, when you're doing the temperature, when you're measuring the temperature, then we care about where the 0 is. But when we're looking at a change in temperature, then we don't care what the 0 is. We just look at the difference. The change would be, you know, what is the difference between mile marker 32 and mile marker 212, and then compare this to mile marker 0 and mile marker 100. And so when we look at the change, it doesn't matter what mile marker we start at. You know, it could be 32, it could be 42, it could be whatever mile marker we want. It's just a change, a difference. Does that make sense? And so that's the difference between this. When we use an equation like this, then we care, you know, what mile marker are we at? Anyway, let's go back to chapter 5 here and take a look at this. There are 2 ways we can do. You know, how do we know the ratios? Well, you know, it depends on the oxygen. Here, this one would have 1 oxygen, this one would have 2 oxygen. And so the weight ratios would be the difference here. The weight ratios are going to be different. And so one thing we can do is like water. Do you know what the weight ratio of water is? Or the mass ratio? You know, we know water is 2 hydrogen atoms for every oxygen. But, I'm sorry? Yeah, so we'd have to know how much a hydrogen weighs and an oxygen weighs, which we're going to do in this chapter. But the weight ratio is actually 11% hydrogen and like 89% oxygen, because they weigh such a different amount. And so there are different ways. To visualize these as weights, you know, if we were to visualize this as weights, it's weird, because then, you know, for example, carbon is what we call 12, oxygen 16, and so we have 32 oxygens for every 12 carbons. And so in terms of weight ratio, then what is the weight ratio? Well, if we call carbon 1, then 12 goes into 32 how many times? 3 times almost? You know. And so in terms of weight, it's almost 3. What is 32 divided by 12? We might as well get the right ratio. 32 divided by 12, 2.6. 2.6. And so if we did this in terms of weight ratio, we'd have 1 part carbon, 2.6 parts oxygen, which looks funny. And so when we visualize molecules like this, we visualize atom ratios, not mass ratios, because mass ratios are weird. When we visualize water, we visualize atom ratios, H2O, not mass ratios. Because the mass ratios could do the same thing for water. You know, these are U's. We talked about U's. Hydrogen weighs 1 U, and we have 2 of those, so it's 2 U, and then oxygen is 16 U. And so 2 out of 18 parts is hydrogen. What's 2 out of 18? 1/9. So 2 divided by 18 is 0.11. And then oxygen, it would be 16 out of 18. 16 out of 18. 0.88. So another way of looking at this is H 0.11, O 0.88. That's in terms of weights. Or I said about, what did I say? 11%? Maybe I didn't say that. Maybe I said 11% hydrogen, 89% oxygen by weight. So again, we don't use the weight ratios, but the weight ratio would stay fixed. Weight ratio would stay fixed, and the weight ratios would be different here. And that's one way of determining it. And your book talks about the weight ratio, which we will talk about a little bit later. All right, so atoms, what we want to know is this. We want to start trying to understand atoms. Yeah, oxygen atom is different than a hydrogen atom, but how are they different, and why are the properties so different? And so we look at an oxygen atom and compare it to a hydrogen atom. Why are the properties so different, and why do they weigh such different amounts? You know, and also the size. The hydrogen is quite a bit smaller than the oxygen, and so we need to understand these types of things. And so, well, the first thing is we need to know the composition of atoms. So let's take a look at the composition of atoms. Because in order to understand properties, we'd like to know the composition and what else? And the structure. Then we'll know about the properties. And so atoms, well, it turns out atoms are made up of subatomic particles. Okay, and then the structure would be, you know, how are these subatomic particles arranged inside the atom? Okay, the first thing is, what are the subatomic particles that make up the atom? Well, there are three. There's the electron, yeah, the proton, and the neutron. And so first, let's talk about the electron, which is here. One is, yes, it is a subatomic particle. And the subatomic particles, in chemistry, the electrical charge is everything, so we need to know the charges on things. And so this says carrying a unit negative charge. A unit negative charge means that each electron has a -1 charge. -1 charge. That's what a unit is, it's just one. So that's shown here. The sign value of the charge is -1 or 1-. Sometimes we write it negative before, sometimes we write it after. I would have written it before. I'm going to call it -1. We give it a symbol. The symbol we give the electron is just E, and this negative here just refers to its charge. It's 1 electron. It was discovered by J.J. Thomson. You know, talk about how it was discovered in a minute. But it turns out, once it was discovered, they determined the charge and the mass. The mass of this is very small. The mass of the electron is 1 over 1837 times the mass of the nucleus. In other words, what we say is that the mass of the electron is about 2,000 times lighter than the proton. Actually, not 2,000, it's actually 1837. And the proton is a subatomic particle as well, but this is actually the nucleus of the H atom. The nucleus of the H atom is a proton. So how did he discover it? Well, you know what a lightning bolt is? And then you heard about the discovery of electricity? Well, it's basically the same thing, except he used a much more controlled lightning bolt. And so let me just show you really quick how he did it. Let's go to Have you ever heard of a CRT?
No.
A CRT is called a cathode ray tube, and we have one here. This is a cathode ray tube here. Do you know what cathode rays are? Cathode rays are the beam of particles that go through a cathode ray tube. And the beam of particles are electrons. These lamps conduct electricity. Electricity they call cathode rays when they're going through a gas, like this. What is this? Yeah, it's
2018 Emmy Awards.
So we see cathode ray tubes. Have you seen neon lamp?
Yeah.
Neon lamps, those are cathode ray tubes. What's inside those? Cathode rays. What are cathode rays? Electrons. These things conduct electricity. They make little lightning bolts here, but these are very controlled lightning bolts like this. And so he studied those, the beams of electrons. And this is a lot easier to study than a lightning bolt, is for sure. And so let's take a look at this one here. This is better. No, it looked good. This is a homemade cathode. I've seen this one before. This homemade cathode ray tube. Oh, what's wrong with the volume?
Vacuum pump I'm using here is made out of an old refrigerator compressor. The power supply is made using a variac and an oil burner ignition transformer. The variac, also known as an auto transformer, allows you to vary the voltage coming from the wall outlet without altering the waveform. The output of the variac goes directly into the oil burner ignition transformer. Normally, an oil burner ignition transformer takes in 120 volts AC and steps it up to about 10,000 volts AC to 23 milliamps. But when I vary the voltage coming into it, I can either lower or raise the voltage coming out. The actual cathode ray tube was built using a wine bottle and some stainless steel wire. I drilled a hole into the side of the glass bottle carefully using a glass drill bit and inserted a wire bent in a half circle shape. Then I secured it with hot glue to make sure it was vacuum proof. As you can see, I made two of them, and they each have the wire different lengths down the tube. To create a vacuum inside of the wine bottle, I just attached a hose bar into the vacuum hose and slipped a rubber O-ring over it. When the vacuum is full, the rubber O-ring sucks down onto the bottle and it just seals itself. This way there is no epoxy or glue needed. Now it's time to power up the cathode ray tube. To do this, we need to attach some electrodes to the terminals of the oil burner ignition transformer. Next, we simply attach one of the other ends to an exposed piece of the hose bar and the other to that wire we added into the wine bottle. Now I turn on the variac and slowly and carefully turn up the voltage. As you can see, a beam of electrons, also known as a cathode ray, appears. It glows a bright purple color in my case due to small amounts of nitrogen and oxygen that are still left in the tube. Now, last time I was just running the tube on an AC current, so this time I'm going to add in a high voltage diode to maintain a half wave amplified current and see the difference in the beam. Now that we have that diode, let's power it up. As you can see, part of the beam that is glowing is only on one side of the tube. Last time it was on both sides, and there's a dark space in the middle. Now I'm going to demonstrate the magnetic deflection property of a cathode ray tube. Since it is a beam of electrons, it can be influenced by a magnet since the electrons have a negative charge. Here I have a few magnets, and one side is marked with tape. When I put one side of the magnet that is marked up to the beam, it bends around it to the right. When I put the unmarked side to it, it bends around it to the left. Now I'm going to switch around the electrodes so that the electricity is flowing the opposite way. Now this time the dark space is on the other side. And when I hold up the marked side, now it bends around it to the left, and the unmarked side bends around it to the right. So depending on which way the electrons are flowing, they take a certain path around the magnet. Now I took out the diode and I'll show you the deflection of the beam when it's running on an AC current. As you can see, the beam appears to split around the magnet. Now, I told you earlier in the video that this is going to be split into two parts. The second part is going to go over the more technical aspects, describing why the beam splits and why it switches directions, if you're interested in that. I'll be using slow motion to analyze the cathode ray tube, and I'll show you in that video the beam function of the beam tube. When I put one.
All right, so we don't really need to. This just gives a convenient way for studying electrons. He had to create a vacuum in here because if there's no vacuum, then you need a lightning bolt. And if you have no vacuum there, does a lightning bolt travel straight? No, lightning bolt has this kind of random path because there's so many collisions, so many gas particles in there. And not only that, lightning bolt would need a lot higher voltage than what he's generating there. He's only generating up to 10,000 volts, I think. But you need more voltage to generate a little lightning bolt in here if you didn't have a vacuum. A vacuum just makes it easier. Okay, now once we have the deflection, looking at the angle of deflection, that's how the mass was determined. Because heavier particles are harder to deflect. Lighter particles are easier to deflect. So based on the angle of deflection, we could calculate the mass. Because do you think they put the individual electrons on a balance to weigh them?
That would be cool.
That would have been cool, but you know, how do you weigh an electron? How you weigh an electron? You certainly don't weigh it on a balance, not even the most expensive. How you weigh electrons is by looking at some physics and the deflection due to electric and magnetic fields. That's how you weigh electrons. And so we can weigh individual electrons this way, figure out how much they weigh. And how did they figure out that this is a part of all matter? You know, maybe it's just only special matter. Well, he made these out of stainless steel. But if you use brass, same thing. If you use aluminum, same thing. So no matter what the metal was, it generated the exact same cathode ray, which means that cathode rays must be a fundamental part of most matter, at least all the matter. So you can put anything, graphite, you'll get the same thing. And so based on those conclusions, came about the discovery of the electron here. In terms of J.J. Thomson. Now, what else is the atom made up of? It's made up of protons and neutrons. The discovery of the protons and neutrons, we are not going to talk about that. You know, if you're interested in the discovery of protons and neutrons, look it up on Wikipedia. How they weighed the individual protons and how they determined the mass of the individual neutrons, we're not really going to talk about that either. And so there are some things that, of course, we'd like to know, and if somebody asks you, you say you don't really know. You know, somebody asked me, I don't know all the details. And somebody did. Protons I know a little bit more. But we look at how those particles are arranged, and so this jumps. You know, what happened to the protons and neutrons? I don't know. We're just jumping a slide. So electron's important. Electron's not so difficult to understand. You can make a homemade apparatus to view electrons. Protons and neutrons are quite a bit more difficult. The discovery of those came later. But how's everything arranged? One person proposed everything's arranged like plum pudding. You know, plum pudding is you have these like raisins. Those are the plums. And you have the pudding. The raisins are the electrons. And the electrons are just kind of spread out evenly in the pudding. This is a plum pudding model. And so everything's just spread out over the entire atom evenly and then dotted with raisins, which are the electrons. A competing model was the nuclear atom model. The nuclear atom model, everything is not uniformly distributed. If everything is uniformly distributed, it's fairly homogeneous or heterogeneous? It's uniformly distributed. Turns out the structure is quite heterogeneous. It's not. And where did this nuclear model atom come up? Did somebody just hypothesize? Today I'm going to hypothesize the nuclear atom model. Now, the nuclear atom model came about by some observations. And the observation that led to the nuclear atom model was this. You know, people hypothesize the plum pudding model, right? You could just hypothesize it. It just makes sense. Everything's uniform and spread out evenly. So that you could hypothesize, but the nuclear atom model came about because of some bizarre observations. So what were the bizarre observations? One is this: a piece of gold foil. Gold is good because it's hard to corrode, it doesn't react much with anything. And gold is what we call noble metal. Then we have a gun like this. You know what this gun shoots? Not bullets. You know what this gun shoots? Not electrons. They're electron guns. You can buy electron guns. I used to have an electron gun.
Atoms.
Not alpha particles. You know, it's not really a gun. You know what they put in here? They put a radioactive atom. This radioactive atom decays, it breaks apart. When it decays, it shoots out alpha particles. You know what alpha particles are? Alpha particles are chunks of its, what we call the nucleus. Chunks of the atom break off and end up shooting out. And these chunks shoot out like this. Well, there's a little hole here, so they only shoot in a straight line. Otherwise, they'll shoot everywhere inside this. This is better be lead here. Although, no, alpha particles are really dangerous. But you know what you need to shield yourself from alpha particles? A piece of paper. A piece of paper will shield you from alpha particles. You know? There's also other radiation that could be emitted, like gamma radiation. You think a piece of paper can shield you from gamma radiation? No. You're going to need lead bricks to shield you from gamma radiation. X-rays. A piece of paper can shield you from X-rays? No. Do you need lead brick to shield you from X-rays? No. X-rays are a little less of a problem, so lead foil should work for X-rays. And then we have one more thing: beta particles. But alpha particles, these are chunks of the chunks of the atom that break off. And these are chunks of the atom. These are very small chunks. And so, being very small chunks, if this were plum pudding, you'd expect, you have something moving quite fast, very small. It should make it through, pudding and shoot out the other side. Right? Maybe it'll be slowed down. Maybe it'll be deflected a little bit. But what they saw is this. What they saw here is that most of the alpha particles went straight through, as if there was nothing there to slow them or deflect them. And so most alpha particles are not deflected. However, some alpha particles are severely deflected. Do you see that? In fact, they bounce off the atom. And so those alpha particles that bounce off the atoms, what are they bouncing off? Yeah, they must be bouncing off something that's very dense, very concentrated. And so it turns out that alpha particles, when these chunks break off, they're positively charged. And so are positively charged particles attracted to what? Negatively charged. But if you have positively charged, are positive attracted to one another? No. And so it turns out they speculated that these very dense parts or components of the atom must be positively charged. And so this is the nuclear atom model. The nuclear atom model came about because of the scattering of the alpha particles. Most were undeflected. Therefore the atom is mostly empty space. These alpha particles go right through it. Some of these bounced off. If they bounced off, they bounced off because of electrical repulsions. A positive alpha particle encountering a positive, what we call nucleus, this is the nucleus, is going to bounce off, positive repulsions. And so the nucleus is this. If most of the atom's empty space, then the nucleus must have the mass, most of the mass of the atom and all the positive charge. And so they figured out that the nucleus contains the protons and neutrons, and the electrons sit out mainly in the empty space. And so these are the basic conclusions from the Rutherford scattering. Every atom contains a small and extremely dense nucleus. The nucleus contains the atom's positive charge. Why? Because of the behavior with alpha particles. And nearly all of its mass. Why? Because the electrons weigh nothing compared to the other particles. Protons and neutrons weigh about the same. Electrons are about 2,000 times lighter. And so all the positive charge and nearly all the mass are contained within the small, extremely dense nucleus. The major volume of the atom is nearly all empty space. The space outside the nucleus is thinly populated by electrons. The total charge of the electrons, which are negative, balances out the total charge of the nucleus, which is positive. So we have electrical neutrality. Electrical neutrality is important. That is, positive charge is equal to the negative charge. And so this is how we visualize the atom. When we visualize the atom, this is space, let's say the atom's about this big, 10 to the minus 10 meters. 10 to the minus 10 meters is best represented using what? You know what 10 to the minus 10 meters is called? Pico is 10 to the minus 12. Pico. Nano is minus 9. And so if we're looking at 10 to the minus 10, let's say 1 times 10 to the minus 10. 1 times 10 to the minus 10 is equal to, this would be meters. 1 times 10 to the minus 10 meters is equal to, okay, let's go 10 to the minus 9. This would be, if we make this number bigger, this has got to go smaller. So it would be 0.1 times 10 to the minus 9 meters, which is equal to how many nanometers? 0.1 nanometers. Now 0.1, it's a hassle. How big is the atom? Oh, it's 0.1 nanometers. It's a little bit of a hassle, right? How big is that atom? Oh, it's 0.123 nanometers. So nanometers is not good. How big is that atom? Well, it could be, well, let's make this smaller. If we make the exponent smaller, we make this bigger. So we go to 10 to the minus 12. This would be 100 times 10 to the minus 12 meters, which is equal to 100 picometers. How big is that atom? 100 picometers, or maybe 123 picometers. Then we don't need a decimal point. It's a lot easier. There's another unit for that, and that's 10 to the minus 10. 10 to the minus 10 meters is defined as 1 angstrom. Have you heard of the angstrom before?
Yes.
Let's see, angstrom. But the angstrom's not as convenient because, let's say it's 123 picometers. How many characters is that? 1, 2, 3, 123 picometers. If you did the same thing in angstroms, it would be 1.23 angstroms, which means 1 extra character. Although angstrom's 1 character, picometers 2 characters, so there's a trade-off there. But a lot of people don't like saying 1 point, it's a hassle. A lot of people just like saying 123. It's less hassle, the same number as big. So the diameter of an atom is about 1 angstrom or 100 picometers. How big is the nucleus? Well, if this is 100 picometers, how many picometers is the nucleus? If the atom is 100 picometers, how big is the nucleus? In picometers. So take 10 to the minus 14 meters and convert that to picometers. What would it be? 0.01. So 0.01 picometers. So this is 100 picometers, this is 0.01. It's how many times? It's 10,000 times smaller. And so the analogy comes like this, and it's in your book, but you know what? I forgot what ball it is. If the atom is one football field in diameter, then the nucleus would be, I think, a golf ball in size. And so the nucleus would be a golf ball, the atom would be a football field. But I need to double check that. I can do the calculation, but I don't want to do the calculation. The golf ball, how big is a golf ball? We could just do a ballpark calculation just to check that. The golf ball is about how many centimeters? Actually, I don't know. I don't play. I used to. It's about that big. A couple of inches?
4 centimeters.
4 centimeters? Okay, 4 centimeters. So let's say the ball is about 4 centimeters. Okay, and then a football field is 100 yards. And so we need to get this in the same, let's see if ballpark we're in the same range here. So 100 yards is how many centimeters? 100 yards is how many centimeters? So, you know, this is the classic dimensional analysis problem. You know, how do you figure out that? I don't know. Well, we just try. So the strategy is, I don't have a map in my mind. I'm just going to try to cancel out yards. And so what do you know about yards, and what can you change it or relate it to? Yeah, okay, 3 feet. 1 yard. Yards cancel. And then I just start over again. Now I got to get rid of feet. And so I'll just go feet to inches.
That's 9,144 centimeters.
I'm sorry? And then I'd go from inches to, yeah. And so you don't have to have a plan laid out. 2.54 centimeters per inch. So how many centimeters is a football field? So 100, we could do a ballpark, but I'm just going to calculate. 100 times 3 times 12. 9,144. Thanks. And so this is about approximately about 1 to 10,000. 1 to 10,000, which is approximately the same thing here, because if we're going from 0.01 picometers to 100 picometers, then the difference is 10 to the 5th. Right, that's the difference, 10,000. So it's about right. So the golf ball to football fields, we're about right.
Well, goal line to goal line.
Yeah, okay. That's, yeah, goal line to goal line, not the end. Diameter of an atom is approximately 10,000. Well, I didn't mean approximately 10,000 times. Okay, combining results of the experiments with the nuclear model. Okay, these are some of the conclusions of the observations. What was that? The nuclear model came from what? Was that the cathode ray tube? Where did they figure out the nuclear atom model? Was it the cathode ray tube, or was that the Rutherford gold scattering? So the ultimate conclusion, this is from the Rutherford scattering experiment. Most alpha particles were not deflected. So what does that mean? The atoms are mostly empty space. Fraction of the particles slightly deflected as they pass close to the nucleus. Particles near the nucleus are repelled by positive electrostatic forces. Small number of particles on the collision course with the nuclei were repelled backwards. They were repelled backwards because of the positive electrical repulsion. That was the force that kicked them back.
Since atoms are so tiny, would the space between the nuclei and the electron be a vacuum?
Yeah, exactly. Empty space. True empty space. So what were the other subatomic particles? The other subatomic particles are the proton. So discovered by Rutherford. We're not going to get into it. Also positive charge. So the proton's given P or P plus. It's about 2,000 times heavier than the electron. It's much more massive. And then we have the neutron. The neutron has no charge. It's neutral. Its mass is about the same as a proton, about 2,000 times heavier than an electron, or about 1 U. The mass of a proton is about 1 U. The mass of the neutron is about 1 U. The mass of the electron is like 0.005 U. Symbol is N or N0. 0 for the charge, no charge. Okay, Chadwick discovered the neutron. You don't need to know. And Rutherford discovered the proton. You don't need to know how those were discovered. But it's interesting. Yes. All right, so first we're going to look at the composition of these atoms and a little bit about the structure. And so here we have the nucleus in the center. Nucleus, this contains protons, which we call P plus, and neutrons. Not all nuclei have neutrons. For example, hydrogen, there's only a proton, no neutron. Actually, this is only one. All the others contain neutrons as well. Protons and neutrons. Maybe I should put an asterisk, except for hydrogen.
Shouldn't that rebel?
Yeah, hydrogen only proton. And then we have the electrons in empty space. All right, so since most of the mass and all the positive charge, so all positive charge and most mass. In the electron, this is all the negative charge, and not much mass. So, what was the density of gold? About, just roughly. Okay, 19.3. About, just roughly about 20 grams per milliliter. 20 grams per milliliter. Do you know what the density of the nucleus is? If we calculate the density of the nucleus comes out to very small. The density of the nucleus comes out to 2,000 tons per milliliter. 2,000 tons per milliliter is ridiculously big. Ridiculously big. That's way more than gold. But why is it way more than gold? Because gold atoms consist mostly of empty space. So, and so we want to know, first we want to know the numbers of these things. You know, how many? So how many? But we're missing something. You know what we're missing? How big? How big is a proton? How big is a neutron? Well, it's got to be small, right? If you have them crammed in the nucleus, so those are small. How big is an electron? Does anybody know how big an electron is? Like, it doesn't weigh much. It's 2,000 times lighter. 2,000 times lighter than a proton or neutron. But how big is it? Is it bigger than a proton? Smaller than a proton? You'd think it's smaller than a proton, but if somebody asks you how big an electron is, you know what they'd say if you ask a physicist? could watch this on Halter and Collider. You ask a physicist how big an electron is, they'll say it is. It has no volume. The electron has no volume. But that's in physics. So we ignore chemists. They just ignore it because it's too abstract. You know. It has to do with Higgs boson particles. Have you heard all that stuff? Yeah, we aren't gonna. What is mass? You know, that kind of stuff. And so we're just gonna ignore the size of it right now because it has no size basically, which is a weird concept because you'd think it has some size to it. And so the question is, the protons and neutrons for sure you think they have some size to it. But what is important for size is the size of the atom. Is there any uncertainty in that? Well, not like the others. And so what we're going to ask is how many protons? Well, how many protons is easy. We have a number for that. The number of protons is called atomic number, and it's given a letter Z. Symbol Z. That's how many protons. How many protons? Z. Z is the red number on the periodic table. You see the red number up there? So let's pick one of those. I'm going to pick francium, FR. How many protons does francium have? 87. 87. If you can't see the periodic table, it's 87. It's a red number on there. 87 protons.
Isn't that number also unique to the atom?
Yeah, right. We don't have to have Z defines the element. The number of protons defines the element. And so what we say is that element number 87 is francium. What do all francium atoms have in common? 87 protons. Okay, let's do another example here. Oxygen. Oxygen is, do you know what element number that is? It's not element number 16. Yeah. It's element number 8. We'll just take a quick look. We're running out of time here. Periodic table. Let me put it up on the overhead so you can see. I see here. It's element number 8, which means, yeah, 8 protons. Now, oxygen also contains, yeah. We have, in nature, there are 3 different oxygens. Found. In nature, that just natural. These occur naturally in water. So the water that you drank today had 3 different oxygens. One oxygen we call oxygen 16. The other oxygen we call oxygen 17. And the third oxygen we call oxygen 18. And their composition varies. All these have the same Z. Z is equal to 8. 8, 8. Therefore, they have the same chemical properties. Yeah, same chemical properties. And so the number of protons seems to dictate the chemical properties here. But they have different number of, this is number of protons. They have different number of neutrons. The number of neutrons, which we'll call capital N here, is this: 8, 9, and 10 neutrons. And so it has an extra neutron. It's going to weigh more because neutrons weigh. The number of electrons will be the same, Z here. The number of electrons is 8, 8, and 8. And so these are the compositions. And so if we take N plus Z, we get A. Have you ever heard of A?
Yeah.
A is called the mass number. And the mass number is the number of protons plus the number of neutrons. So A is equal to Z plus N. Z plus N. And so the mass number of this would be 16. That's this. This is A. Mass number for this is 17. The mass number for this one's 18. So chemically, these behave the same, but some are a little heavier than others. So having that additional neutron or two doesn't impact it chemically. Chemically, it's going to behave the same. And so we'll look at these. These are called isotopes. So we need to know how many protons, neutrons, and electrons this atom has. And we're following this. I want to talk about protons next and then neutrons, so I'm just going to follow along the board here. Yeah, we'll end here. See you tomorrow.
Oh, okay.
So everyone's here.
I'll see you tomorrow. Have a good day. See you tomorrow.
See you tomorrow.
Difference between pressure.
There's a YouTube video of this. boils down to this. Where the zero marking is. If you have an empty tank of gas, let's see, do I have an empty tank of gas? Look, you know what? Can you ask me at the beginning? I'm going to show a demonstration of this. Ask me at the beginning of class tomorrow. I'll demonstrate the PSI A versus PSI G.
And I have one more question.
Okay.
Like the combination, like P1 V1 over T1.
Combined gas law.
Yeah. So